everyone who's all here. I see Reed and Anna in the chat. Let's throw 100 points. Mewbot's awake. Doing a lot better today. One of these days I'll shave. Thank you so much, Reed. I appreciate that. Doing a lot better. I'll tell everyone if I have to go. Hopefully we're fine. But doing a lot better today. Getting back in the swing of things. Probably back at like 80, 90%. Let's hope we are. So with that, we're going to do some multiple regression here. If you're from 201, we'll be probably doing a 201 stream to help them out here in a little bit. Look better next week. We'll fix this over the weekend. So let's hop over here and start doing some regression. Let's do it. Okay, so here we are talking about some multiple regression. I'll make it bigger so I can see what's going on. And we've got the launch product data set. So the launch data set right here is going to use a bunch of different variables. And please ask any questions you have at any time during this. You need to have library reg class loaded up, so make sure to have it installed. If you have problems, please contact us immediately. These are just warning messages. Psst, warning messages. No one cares about those. So we're going to load the launch data set right here. And this is because it's a data set already pre-installed into R. Please note that when you look at this, it tells you it's from the reg class package. Now, once again, if you have any questions at any time, please let me know. But this loads it right here. This is not an Excel file. This is like pre-loaded data. If you ever want to see all the data you have access to, here's every data set you have access to by typing data. Yours is probably different than mine because I have a lot of different packages that currently give me more access to more data. So with this right here, we're going to look at the profit, and we have different characteristics, X1 through X crazy amount. These are all just different X variables right here for the profit from a certain, for 652 products released in the market. Wow, pretty crazy. So let's go ahead and take our data right here. And what we're going to do first is we're only going to get the first 10 predictors. Now I need someone's help right here. How do we go in and look at the rows and columns of a data set? So I have a data set right here. And I want to look at the rows and the columns. While you're thinking that over, I'll show you some cool commands. How do we look at the rows and the columns of a data set? Here's all the variables. Whoa, it's a crazy amount. Glimpse gives us a great job, Reed, right there. Excellent, Reed, 100 points. Keep getting those points. So Glimpse lets you glimpse a data set, which gives you just an overview of every variable inside of it. It's like structure. You can see most of the variables look to be categorical. They're not set that way, but they're like integer ones and zeros. And then we have some other variables that have more variation in them. And we have a profit variable right here. Veda, excellent work. Let's go here to launch. Now, once again, we're not knitting this. Watch out. This would create a lot of output. We're going to go right here and take rows 1 through 11. This is just a vector of rows 1 through 11. And it's going to take rows 1 through 11. A lot of printing going onto the screen, but we can see what we've created right there. And let's call this product launch and save into it. So hopefully this is good practice right here, and reading this code makes sense. Save into product launch, so it's PL product launch, and take all the rows because we're leaving it blank, and then take the columns 1 through 11. Veda, excellent work, 100 points. Keep it up. Keep practicing. Try solving these things along with me, even though I'll be showing answers right here. Make the scatter plot matrix. So with the scatter plot matrix, we're going to use the pairs function right here, and there's additional arguments you can use to change the points. This is point style. It's not character. Timothy, Connor, where you at? Connor Moore. He told me what PCH means. It's point style, but we'll take a look at that right here. So we need to use the tilde dot. Pairs, profit, tilde dot. Now, why is profit right here? Good question. It's the what. Why is profit right there? We haven't finished the code yet. We always want to do... I'll finish the code. This is not quite everything we want, but it'll get us there for decent. Why is pairs in that position? And then what does the dot mean? It literally will tell you up there. It's the, gosh, great job. Good practice. So this means show me the combination of the y variable at the top with all the x's and make a scatter plot matrix. The other arguments are not necessary. They're just to make things look nicer because we got some really big points. We're going to try to make this look pretty right here. So I'm decreasing font size and stuff like that so we can actually get a decent visualization of it and maybe talk about what we see. CEX is character expansion, which controls the size of the points so you can make them really tiny. Look at them. They're going to get tiny. There we go. Look at that. Much better. And PCH is point style. I'm choosing my own. I want to choose what I want. So it's going to change the way these points are, a different type of point. You'll see it change here in a second. Did it change? It might have changed. But this is a different type of point. and it's going to change the way the points look. It's very hard to see because they're so tiny, but it is changing what the point is. I'll show you really quick. Plot 1 through 10, PCH equals 10. Just so you can see right here, and let's make CEX. CEX is going to make this bigger. So you see how it's bigger, and if I change this, the PCH changes, so we get some stars, but PCH changes what they are. Great job right there, Veda. So PCH right here is an argument that changes the way the points look. It might be hard to see if they're really small. CEX changes the size, stands for character expansion. So that's just a size, just it's saying what size. Why don't they call it size? I don't know. Character expansion, because that's a character, and how much do we want to expand it? So we are choosing, and the important parts of this code, let's relook at the code right here, our actual code. We are saying y tilde x comma data equals classic, and then we are choosing to increase or decrease the point size, and then we're choosing point style 14. So PCH I call point style, and it looks something like this. Now the most important thing right here is it the first row, the second row, the third row, the fourth row, the fifth row, the sixth row, the seventh row, the 10th row, the 11th row. What row is the most important when you do this pairs function with y tilde x? Just need one number in the chat right now. When you do this, why would we make a pairs right here with all of our x's and our one y? We really want to examine what right now, which the questions will go over. We really want to examine what right here because there's a very important thing when we do linear regression related to the y and the x. So when we do linear regression and we're analyzing a y's relationship with other x's, the most important thing right here will be to analyze from this the what. When you see this, you're like, I really should look at this because this is going to be my y with each of the x's. The first row, Veda, just keep getting those points. So right here, you see profit's relationship with x1 is kind of non-existent. Profit's relationship with x2 is kind of a somewhat linear, but a little bit of bend. Profit and x3 have a pretty decent linear, a little bend at the air. Profit and x4 have more of a bend. Is everyone seeing what I am seeing when I see like a bend right here? Does that make sense? This is a little negative, maybe non-linear at the end, non-existent, negative, maybe a little non-linear, negative. It's like if you imagine a line going through it, does the line go up or down? This line really doesn't look to go up or down. This one might go down just a little bit, kind of weaker. Now, there is a way to find out the answers to this, of what is the correlations. And anytime I pull a library right here that you don't have, you would need to do, if it says you do not have this, you would need to do this. Oh, doesn't like it. I swear. It's one of my favorite plots to make. It's such a cool plot. I'm going to look it up really quick right here. Ooh, that's pretty. Which one is this? Oh, wow. No way the pairs does this. Oh, you have to do way more. They've got a really cool thing right here. I got to show this. I didn't know you could make things as pretty with the pairs as this. Check this out. This is the pairs function. And, ooh. Oh, they need to make the other one. Wow. So I really like this right here, and we don't have to make something like this. But the whole point right here is when you do the pairs, you're looking at the correlation between like supple length and supple width. And they're actually coding it by different flower types in here. Then they're also increasing the font size based on like a conditional, like how strong is the correlation right here. So the stronger the correlation, the higher the values. I hope if it's negative, it would be big too. But really neat plot right here using the pairs. So beautiful plots. This is not our data, but we're just looking at combinations of the variables. And it also shows the categorical. If you look right here, this plot in this region, which is supple length and petal width. So supple length and petal width, petal length, supple length and petal length right here has a very strong correlation. Also, this one down here, if you look at it, petal length and petal width has a correlation of this. These ones on the other side are just a mirror image. So we had the same thing going on with our images. It's going to load that big image here in a second. But the whole point of the pairs function is to look at bivariate combinations of variables. And you notice these plots are just mirror images of each other. So sometimes people use the pairs to give the correlations down here. And I thought I had a really quick way of doing it with the GG. 2 seconds, I'm going to see if it has it. I thought it did. 2 seconds. Oh, it just takes the data. Here it is. It just takes the data. It's that simple. It doesn't use a y tilde x format. So we're going to get a similar, it's loading the graphic right here. It's making all the plots. And we'll get a similar graphic right here when you actually see the correlation. So here you can see the correlation is the strongest. Here's a very strong one. The correlation is strongest between profit and X4, which is the plot right here. And so you see the positive strong correlation. It does flip the graphics. There might be an argument to change this, but you can see weaker correlations right here like X6, and X6 is right here where it's a very weak correlation. So we can actually get the correlations very quickly with the GG pairs and find out what's going on. So I love stuff like that. Name one of the predictors that looks to have a strong relationship with profit. So actually right here, pretty easy to see which one has a strong relationship with profit. Who can tell me, looking at this right here, which one has a strong relationship with profit? Just go across. Give me one of the X's that looks to have a strong relationship with profit. So this makes our life very easy. And then we can look at the plot. Aloha Ditto, good to see you here. Which one of these looks to have a strong relationship with profit? Because we're just looking right here. Here's profit. And then we go to the X's. Profit's right here, actually, because it's this way. So which of these X's look to have a strong? X3, yep. And then you could look at it right here. Here's X3. Does that make sense? Profit and X3. And it looks like it does have a strong relationship. Yep. Name one of the predictors that looks to have a weak, non-existent relationship. So go ahead and name another one. Veda, another 100 points. Let's just keep racking up those 100 points. What is a predictor that has a weak, non-existent relationship with profit? So once again, profit is the y variable of interest. So we're going to assign it to the y variable. And then we're just going to look across here and say weak, non-existent. Let's go for the weakest, most non-existent relationship. There's a lot of them in the running right here. There's a lot of them that are kind of meh. There's a lot of ones that are not that strong, like they're very weak. And weak means close to 0. Review of correlation. So which of these are very weak, have really nothing going on? So the ones that are very weak and have nothing going on would be close to 0. So what's one of the ones? I actually have one I like more. It's not the weakest, but we should see some weak, non-existent relationships. And then we could point to the plot between the X and the Y. I like this because it makes it really easy to see which ones are very weak. You can actually tell statistical significance on this. X1, yep. I like X1 looks one of the worst. It is not quite the weakest. I do agree. I was looking at X1. X6 is, I think, the weakest because it's the closest to 0. X10 is also super weak. The more stars it has, the more statistically significant it is. I think this might actually be significant at the 0.05 level. X6, great job, everybody. X6 and X8. X8 is more moderate. X8 is going to be this plot down here, which has a moderate negative or weak negative correlation, maybe weak, which it says weak. That's worth another 100 points. It's not super weak, though. The stronger ones are going to be this one, this one, this one. X2, X3, and X4 are your strongest. And then weak are going to be X5, X7, X8, 5, X7, and then non-existent nearly are going to be X1, X6, and X10. And this one's weak, non-existent. The closer it is to 0, the weaker it is. Doesn't matter positive or negative, that just indicates direction. Name one of the predictors that looks to have a non-linear relationship. Oh, do you see what I see? Which of these looks to have a non-linear relationship? Pretty easy to see if you look at this right here. One of them definitely has what looks to be a bend, or another one. I'd say 2 of these look to have non-linear. What you want to do is you want to pretend you're drawing a line through this. And does a line go through it, or does the line have to bend to go through it? We're looking at profit with one of the X's, even though this is flipping the axes. X4, and I was also looking at X4. X4 looks to have that bend through here too, and X2 looks to have a bend. You can actually cheat and find the answer to these. We're just doing a simple regression right now. I'm going to show you a trick. Watch this. Well, first off, let's visualize our model. So here's the model, and does that line go through it? No. This function we'll be learning next week, the choose order function, and the choose order shows you higher order polynomials, if you can get it to run. The choose order is going to see if a higher order polynomial goes through the data. So x2 looks like it needs a higher order polynomial that would bend through the data. x4 looks to have maybe a bend at the end, and take a look, it does. So there's maybe a bend through x4 because the line maybe doesn't do as well, and we'll be going over these next week on how to use the choose order. But all we're looking at right now is we're just thinking about, does a line go through the data? Does a line go through this? Maybe not so well. Does a line go through this? Maybe not so well. It kind of bends. And once again, if we had a function like this, we can actually see what the higher order polynomials would look like to see if they make a better fit. And they definitely look to make a better fit. Look at that R squared adjusted. So yeah, it looks like we have some nonlinearity to deal with. Fit the regression model with the LM. Use the y tilde x comma data equals. So let's go ahead and do this right here. So we're going to fit every single variable. Profit tilde dot comma data equals PL. Run the check regression. Check regression just takes the model. Coding got a little bit easier. And you know what? I'm not shocked on this. Here we'll go. Where's the problems at on this? Where are the problems? Explain to me just briefly where the problems are at. Could you summarize where the problems are at? Take a moment. Feeling a lot better today. Don't worry, Brian's not doing nearly as bad. Yesterday was. I thought I was fine today. And that got bad. So when you do a check regression, let's write the steps down because maybe some people don't know this. Step 1. So when you do check regression, you check the p-values to see if any are below 0.05. If they are, you fail those tests. Well, explain greater detail, Veda. So when we do this check regression, we want to use our regression, but our regression needs to be a reasonable reflection of reality. And we're going to see if it meets the conditions of linearity, meets the condition of equal spread, and meets the condition of normality. And linearity needs to be met for every single x and the overall model. Now, a lot of times you can't do it for the overall model because you need duplicates, which means you need repeated values of the same x's to run the test. And so it's literally telling you, I just can't even run this test. We can look over here to see if it meets it, though. We can see if that line goes through the data. So this test just couldn't even be run. It just said, nah, I'm not doing that for you, which that's not bad. It just means we don't know the answer to it. We have no way to, other than looking at it visually. The p-values for the linearity test. Oh, yeah. Sorry. So, yeah. X1, X3, and X6. Yep. So that's good, right? So I meant all their X's of those fail. Yes, Veda, that's exactly it. Veda, great answers. That's exactly it. Yes. Veda put it perfectly. X1, X3, and X6 are the only ones that pass linearity. There's problems with the linearity here. We don't know about the model. And then we have problems with equal spread, and we have problems with normality. Is our sample size greater than 25? Because that's what we do next. Is our sample size greater than 25? We saw that there are issues. That's step 1. We failed any test that's below 0.05. That usually confuses people. Make a note of that. If the test has below 0.05 p-value, that's evidence of a problem. The null hypothesis is that we're good on any of these tests, and the alternative is that we're bad, so we have evidence of a problem that there's bad things going on. So with these p-values right here, we will need to investigate any p-value below 0.05 if we have a large enough sample size to continue. I need to go to live chat. I forget. So can we continue? We are on step 2 to see if we can continue on. Can we continue on? It tells you down here about that. It tells you about step 2. Can we continue on? Do we have a sample size of at least 25? Do we? How would we know? And the whole point of this is because if we don't meet certain conditions, our model is just number mathematics stuff that we shouldn't be doing. It's weird to say, but it's like the only way this model works is if it reasonably reflects reality. And these conditions check to see if we reasonably reflect reality with what mathematics we're trying to use to describe the world. And our sample size here, right here, is greater than 25. That means we get to continue to check the diagnostic plots. Now we need to add something else right here. I think it's extra equals true. And the extra equals true, we can now look at each individual plot right here. It's going to do 3 at a time. And let's take a look right here. Ooh, these look good. Maybe there's a bit of an issue on X2. I'm worried about X2. Do you see how X1, the line looks to go through the center? On X2, maybe there's a little bit of a bend. X3, there's a little bit of a, not that bad. I'm worried about X2. I should write that down. I'm worried about X2. X4, I'm worried about. There's this at the end, so X4 is still showing issues. Wait, remember back in the day when we talked about X2 and X4 having issues? Looks like it carried over. X5 and X6 look all right. We might not even needed to check one of those. X6 we didn't need to check, but it's fine. No wonder X1 and X2 look good. They actually, X3 passed. So now over here, I see it on X7. X7 has nonlinearity towards the end. You can see how the data is kind of curving upwards. X8 looks okay-ish. X9 looks okay-ish. What I'm looking at is I'm looking at this line and asking, does it slice through the middle of this? Like, are the points going around it on both sides, not like this right here where the points go upwards at the end? Because that would indicate the line would have to go up to go through the middle of these. Last plot right here looks pretty good. This line is going through the middle of the data at all times. Once again, let me show you the really bad one right here. It was X2 and X3 where it was really bad. So here, the line would have to go up to go through the middle of these points. If you look, the middle of these points up here is somewhere over here. The line is not going through the middle. It would have to go like this, so there would need to be a curve. X4 was also one of the worst ones too, especially at the end right here, because the line would have to curve. Does that make sense, Veda, what I'm looking for? I'm asking, does this line right here, which is the linearity condition, go through the middle? And it's not going, it would need to be here, it would need to be here, and it would have to be here because there's only 1 point. 1 point is not a good idea to get ideas for linearity from, but we do not see the line going through the middle, especially as you go further out. It would have to start to dip down to go through it. These other ones look pretty decent, like this is at the middle of all this, this is at the middle of all this. So yeah, that's what we're visually assessing right here when we look at the linearity. And then the first overall plots, this plot right here is the linearity of the overall model. Pretty good. It's just when we do this, so before doing the eye test, what do we look at before doing any sort of eye tests? Before doing a visual inspection, what do we always look at? Before we get to any visual inspection, what do we always do? Before we get down to the visual inspection component, we always look at those p-values. Yep. So you start by looking at the p-values to see if you need to investigate. And so we didn't need to investigate this plot. We don't need to investigate this plot or this plot. We need to look at the equal spread right here, which asks, is the spread around this constant? It's not great. It gets like smaller at the end. It's kind of weird. Don't love it. Linearity looks to be one of the major issues. But tell me, how does this normality plot look on the very far side? Why is this plot looking good or bad? Now, we failed the test. This is where your eye has to come into play. We failed the test. We have failed the test for normality of residuals. But how does this plot look? We should make this a written question. I think most statisticians should agree to this. I'd be very sad if they said something different than what I think about that plot. So what would... Yeah, it looks good enough to me. Reason being is it mostly follows this red line. These outer lines are kind of like, it's okay. But if there's points that are a little bit outside, that's not a problem. We're looking for major deviations or major problems. This just barely failed. And then when we look at the normality of the residuals, looks pretty normal. Exactly, Reed. Great job, Veda and Reed. Keep getting those points. Keep practicing along right here. So overall, this looks to have a problem with the linearity. Linearity looked to be one of the bigger issues throughout this. So we could maybe handle that with some transformations and stuff. So P-value for the overall model, because we don't have enough replications. Equals price fails, so we did it through LM. Took the argument, extra true, we did that. Oh my gosh. The regression model looks like a reasonable fraction error. Run the summary of the model. Here we go. I'd say it's iffy. My view on this one is that it's iffy. It's the linearity is where I have my most concerns. The normality of residuals was fine. The equal spread is fine, but I'm worried about linearity. Is the model statistically significant? Where do we look at to know, is our model statistically significant? Where do we look to know, is our model statistically significant? Tell me in this output, where can I, it's a lot of output. We got a lot of output right here. And all we're trying to say is the model itself statistically significant? So where do we go to know, does the model, the whole thing, explain a portion of the variation in profit, because we're trying to understand profit, that is unlikely by random chance, that we're able to know things about profit using these variables that is unlikely by random chance. There's a value on here that says, yeah, that we're definitely doing that. The amount of variation we have in profit being explained by these X variables is unlikely due to random chance. And that is where on this screen? Where is that value? Yep, p-value, and it's good it puts it at the very bottom. It's like the end-all, be-all of the whole thing. Great job right there, Benson. Excellent work. Benson, 100 points for everybody. The p-value on the bottom right here is the p-value of the overall model. So it's important we know, we'll probably going through a lot of this output right here, so very important output to talk through. This is the p-value for the overall model, telling us that our model reduces the sums of squared error by a large portion that we would not expect by random chance. So is our model statistically significant? Yes. And statistically significant just means less than 0.05. But this p-value is the p-value for the model. Now, something I want to point out, and it's very important, when you run a simple regression, if you just do a simple regression, good. Using just a simple regression, the p-value for your x is the p-value for your model, because the slope of the x variable will be the significance of the model. In simple regression, these two p-values are the same. Does that make sense? Like, this is the same as this, and this is simple regression. But in multiple regression, your p-value down here, now it's not like some sort of dividing and adding up of them. It's not, doesn't work quite that way. But it's an aggregate of all of these right here on whether or not your x's together make a significant model. So it's not just one of them anymore like it is in simple regression, but the p-value down here is, in a way, based on these. Now, there's a lot of interesting things that can happen where you have insignificant variables in your model and you have a significant model, but for the most part, this p-value down here is going to reflect the significance of p-values in your model. Don't bring in a stat theory person because they'll start yelling at me some multicollinearity stuff, and we will talk about that. But this p-value down here is the significance of everything working together to make a model where these are just the individual variables. The intercept, nobody cares about you. You're not an x variable. That's why the p-value down here is just of the x variable in the model in the simple world. So let's go back and keep talking about this multiple regression model and make sense of what we're seeing. So with this summary, we need to rerun our model right here. Where did the model go? There we go. Here's our multiple model. Which predictors are statistically significant? And then we'll talk about what this means. So what predictors are, well, what's a quick way to tell if a predictor is statistically significant in the model? And look down here. Got a quick way to kind of tell. What's a quick way to tell if a predictor is statistically significant in the model? Basically, the more stars it has, the more statistically significant it is. I don't always use these, but the dot is going to be, it's less than 0.1, which is not statistically significant. So as long as it has 1 star, it is statistically significant. If it has 2, it's even more. If it has 3, it's even more. So the 1 star is when you have at least a 0.05. The 2 stars when you have at least a 0.01. And the 3 stars is going to be when it's 0.001. So this right here, p-values between these ranges are going to have these denotations. So a really quick way to look at it is, does it have stars? And then what does this mean? We need to talk about that. What does it mean that x9, or let's go with something that is, what does it mean that x5 is statistically significant? Very important question. what does it mean that X5 is statistically significant? So if you notice, the p-value of X5 is different. X5 has a p-value here of 0.000118, and here it has a p-value of very, 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 very tiny, 0.0000 tons of zeros, 262. So in the simple world by itself, it's actually the model. It's the full model. But here it's working together with the other variables to make a model. So when you're in the multiple world, what does it mean to be statistically significant? In the multiple world, to be statistically significant means what when you come to the model and say, here's the information I have? In the multiple world, if you are statistically significant, it means you do what? Now, please make sure you know this. See if you can fill in my blanks. Very important idea right here that when you get to the multiple world, if you are statistically significant in the multiple world, you have brought with you this to the model that the other variables are not accounting for. The part of the variation in profit can be explained by exactly. Great. It's a great. Veda, I'll take that right there. So what Veda is communicating well is that X5 is bringing with it information that the other variables are not accounting for. So that is the portion of it's not literally the portion, but it tells us that X5 explains profit in unique ways that the other variables are not accounting for. And this amount of variation that X5 accounts for that the other variables are not accounting for is unlikely by random chance. So if we take something like X9, which is not statistically significant, watch this. I'm hoping it turns out this way. X9 is statistically significant. But wait a minute. Why is X9 statistically significant here? Take a moment and think through. X9 by itself has what for profit? X9 by itself has what for profit? X9 right here is statistically significant. And what does it mean in this simple world that X9 is statistically significant? Up there by itself, it is statistically significant. So here it is, and here it's not. Why? So by itself, it was statistically significant in a model where it's working alone to explain profit. And then down here on the bottom, it is not statistically significant. It's the same thing. Think about how in the simple world, you're just working by yourself to do something. It's like if we all join a team and say, let's build a house. Well, if you build a house by yourself, you got to do a lot of the work. And maybe you'll do a lot of the work. You'll do a significant portion of the work, unlikely by random chance. But down here in this team, you're working together on the team. Sorry, it's me. It's me because, yeah, everything. So down here at the bottom, it means that X9 now, with the other variables in the model, is not bringing with it enough new information. A variable can be significant by itself, but when you hold all the variables equal, when you include other variables, I would say. So I'm going to, Veda, excellent work. Keep those answers coming. A variable can be significant by itself, but when you include it in a model with other variables, the information it brings might not be unique enough or new enough or explain portions of the why, this is all I'm trying to say, that the other variables are not accounting for. So it looks like maybe X9 just it's not doing enough work here. We have other variables that are doing the same work. X9 is like, I know how to paint, and everyone else is like, I can paint too. Well, this person doesn't really do much. They're like, I can eat lunch. I'm like, well, everyone eats lunch. We don't need you here. Have you covered? Yeah, we have, Chloe. Let me get you that. I'll get you that here in 1 second. Thank you, Chloe. I'll put that. Chloe, email me since this is a public video. I don't put links to the classes in public videos, but Chloe, email me or Discord me. I'll send you the link. We did the Canvas content in the afternoon class. So the afternoon class on yesterday, we did like a lot of versions of it. No, on Wednesday, right? Gosh, days are slipping away from me. But no, Chloe, email me and I'll make sure you get that. Thank you, Chloe, for asking. 100 points, Chloe. I appreciate it. Please ask the questions. Then you know the answers. So a variable can be statistically, you're welcome, Chloe. A variable can be statistically significant by itself. A variable can be statistically significant in the multiple world. But here's the weird thing. Can a variable be statistically significant, not be statistically significant by itself, and then statistically significant in the multiple world? And the answer is yes. Because maybe, I want to think about this. Would it be a great party if I just brought napkins to the party? Brian says, we're going to throw a party. I'm going to bring 100 napkins. You say, dude, we need food. Well, what about if we throw a party and there's pizza, there's hot wings. We got to have hot wings. There's Cheetos. There's hot dogs with ketchup, all that good stuff. Or mustard. I like some mustard, some good relish. And so we bring all these things, and then I bring napkins. So napkins by themselves are not significant, but now napkins at this party with everything else are significant. So in some instances, something might not be simple in the simple world by itself, but then in the multiple world, it does things that the other variables are not doing. You don't eat napkins, at least I don't. So when we think about what napkins do in the multiple world, they bring in unique variation that the other variables are not accounting for. So it's very possible to have these weird scenarios where something is not significant in the simple, is significant in the multiple, and any which what combination you can have. So there's lots of different combinations. What is the value of r squared and what is the value of r squared adjusted? So r squared, and Stats 1 should know this, is the percent of variation in y explained by the variables in the model. So 70.15% of the variation in profit is explained by the x's in the model, or the model explains 70.15% of the variation in profit. Let's write that down. So that is what we have right there. 70.15% of the variation in profit is explained by the variables in the model. But what is r squared adjusted? Just like decision trees for Stats Tool 1, when you add x's to a model, what happens to r squared? When you add x's to a model, what happens to r squared? When you add x's to a model, what will always happen to r squared? Every time you add an x to the model, r squared will do this. Because r squared is explaining, and we have x's that like to explain, or r squared is the percent of variation explained in y by the variation in x. So every time you add an x to the model, r squared will do this. Because we're explaining more. Because we add an x is explained. So r squared must do this. What will r squared always do every time you add an x? You add an x, r squared goes where? Put an x in the model, r squared increases. So every time you add an x, r squared increases. But what is r squared adjusted? Great job, Charlie, right there. Excellent work. Good to see you, Charlie. If you look at r squared adjusted, r squared is adjusted for how many x's are in the model. So r squared adjusted is always r squared with a penalty term on it. So we penalize ourselves for how many x's we add to the model. So if I were to add in more x's to the model and the x's were not to do anything, like they would just be like random. Let's go here, random norm, and 652. Cool. Watch this. PL, random 1. I am literally creating junk variables. You don't need, oh wait. Oh, it did run that. Wow. So what I'm creating right here is some junk variables. Charlie, good to see you. Charlie, I reset the points. No. Here are 5 junk variables. All these variables are completely random. I've appended these variables onto the end of the data frame for random variable 1, random variable 2, and they're all just random normal variables. So now what I'm going to do is I'm going to show you the summary of my model. Here's the r squared adjusted. Because these variables are pure random junk, when I make model 2 with the junk variables in it, what do you think will happen to my r squared? My r squared will do what now? With more x's, my r squared will do what? Because there are more x's, Charlie knows what's going on. Charlie I'm going to throw Charlie another 100 points. Charlie knows this stuff. What's going to happen to my r squared because I added more x's? R squared will do what? Because I added more x's. This model has more x's in it. R squared must do this then. It's currently this. Let's take this. Here's the previous info. There we go. That's what it was on that model. That's awesome. So glad to hear that. Charlie, how many people showed up was there? Was the room pretty full? I'm so glad to hear that. I'm so glad to hear that you enjoyed it. And I hope Dr. Me had a great showing, and I hope the speaker had a great showing too. And really thank you for him giving his time and coming to UT and sharing his experiences. He got in like 1996, did he? Or I was reading through his bio and everything because I wasn't able to attend. It will go up. Didn't go up by much. But take a look. It went up. It has to go up. But what did r squared adjusted do? Probably 20 through 30. That's pretty good. I think the room holds 40. So we'll take 20 through 30. That's a good showing. I like that. That's really good. Hopefully, yeah, I'm so glad, Charlie. Charlie, thank you so much. Glad to hear you enjoyed it. Glad to hear there's a pretty good showing. 20 through 30 is pretty good. I think the room capacity was 40, so we don't want to overbook it. But that sounds pretty good right there. So look at this right here. When we added in the junk variables, r squared went up. And when we go right here, r squared adjusted went down. We don't want that. What is the typical size of the residual? What is the typical size of the residual? We'll use our actual model right here. Do you see the typical size of the residual? And actually, you know what? We'll mention that too. The typical size of the residual is the typical miss the model makes, known as the... Was it Bren's? Was it Bren's? Man, I wish I could have been there if it was Bren's. Oh, but it's for the meeting too. But man, I want some pizza. I want some good pizza. I haven't had pizza in so long. Not like residual. Charlie knows his stuff. These are the same terms right here. Great job, Veda, right there. Excellent work. Both Veda and Charlie know their stuff. Yes, it was. I knew it'd be Bren's. Called that one. It's good stuff. The root mean squared error. Whenever you hear root mean squared error, remember that you just want to cancel the square and the root. And what are you left with when you cancel square and root? Mean error. Now you might say, why don't we just do mean error? Well, if you look at any sort of model, the mean error would be what? What would be the mean error if you just did mean error? So you don't want to do mean error because doesn't tell you anything. Mean error is going to be very cool. It's this. The average error is this. And then we can talk about what we do to it to actually get something sort of meaningful instead of just mean error. Just think about if you were to average the errors for any sort of model, what would you get mathematically for averaging the errors? Because that's what the line of best fit does, is it makes it so the average error will be what? If you were to just average them out, it'd be 0. Great job, Veda, right there. We're just going crazy on the points today. But so what do? We square those errors. So then all of them have to become positive, and then we root them to bring them back to the normal units after taking the mean. You could do mean absolute error. So you could take the absolute value of them and then take the mean of the absolute value. That doesn't weight as heavily on outliers. So if you have outliers, they're downweighted, not really downweighted. When you square them, it makes outliers worth more. So they're more, you don't want outliers. So we like to do this right here. And these are the same terms. So this is the typical miss the model makes. This means when we predict profit, we're usually off by, let me write it right here. I'm going to call this dollars. It's not a percent we are off. It is not a percent we are off. A lot of people say this in percentage. That's not a percentage. That is how much we are off in units of the Y. Whatever this is right here is in units of the Y value. So that's not in a, like, let me try this real quick. Classic stuff. You know what I'm about to do. You called it. Take a moment right here and interpret the typical miss this model makes. Interpret that. Good practice right here. Take a moment. 100 points in the chat. So take a moment. Interpret the typical miss right there. Just look at the Y variable in my model. Remember, this is in units of the Y. You don't really need to know what all is in the model. I can interpret the R squared to say 65.59% of the variation in height is explained with the variables in the model. The R squared adjusted shows us the R squared after we've penalized ourselves for the inclusion of a lot of variables. The model itself is statistically significant. It's down here. We don't really look at F statistic and stuff. That would be the amount of variation we observe being explained versus what we would expect via random chance. We don't look at it so much here. The significant other being a variable in the model does not bring with it new information. When predicting our height are usually close. Charlie, you're right there. Throw in the units of the Y though. So just think about height and think about America. You got it. Just throw in one last word after that because it's how we usually measure height. Inches. Exactly, Charlie. Earning everyone those 100 points. Praxing up some 320. Exactly. So when we predict height, our model will be... Whoa, Charlie. I need some corrections right here. You said will. Remember, it's not going to be will. So take a look down here. We don't want to say will. Be very careful with will because that gives certainty, and our models will never really give certainty expected. Another 100 points. Thank you for the correction right there. It's a conversation up here. So we want to say it's expected or predicted or usually things like that. Like expected is fine too. We expect to be off by about this much. Like that's not saying we will, but we expect. Exactly. Obtain a 95% confidence interval for the coefficient of x1. Did I overwrite my model? I'm always overwriting my model. Where's model 1? I overwrote my model. Cool. Cancel. Just remaking the data because I've broken it. You don't need to do everything I'm doing. I'm doing a little extra because I'm always doing extra. Okay, so we got our model back right here. We need to make 95% confidence intervals. Yep, we have a right model. Just make sure you're using the right model right here. Now, to make confidence intervals for coefficients, Confidence makes confidence intervals for coefficients in a model. The only thing you need to put in here is M, and it'll give you confidence intervals for the coefficients in a model. But I could have told you, they're in decimals. I hate it. I could have probably told you an estimate for these intervals. Because whenever we make intervals, and this is a really good thing for the test, and I need to show you different output to show it. Whenever we make confidence intervals, that was my model too. Whenever we make confidence intervals, how can we make a 95% confidence interval? How can we make a 95% confidence interval? Can you clarify the size? Oh, that's the root mean squared error right here, the residual standard error. Good to see you here. And so that's the residual standard error. That's the typical miss the model makes, or on average, we miss by about this amount. So whatever this is for your model, does that make sense right there? That is the typical miss the model makes. So we're usually off by about this much. Visually, I'll show you this is a different model, but visually, let me show you what this looks like. It's usually about half the width of this interval. If you look how this is 3.5 right here, we're usually off by about 3.5. That doesn't mean we will miss, but the typical residual is usually about 3.5 in size. Like we're usually off by about this, and that's the residual standard error. That's how much we're usually off by. We could miss by a lot more. Like this residual looks to be about 14 or 15. This residual down here looks to be like negative 10 or so, but usually we're off by about 3.5. Doesn't mean we will be, just means we're usually off. You can't visualize multiple models, so it's much easier to see it in like a simple world. A lot of multiple models you can't visualize very well. And so going back down to here, if we have a confidence interval, Professor Emery said it can be calculated by doing the square of the standard error of the root. Hi, Betty's right. Calculate by doing the square of the standard error or root. I forgot which one. Well, so what you can do, he might have been talking about, so we're still talking about the root mean square error. So think about this. We want the error. What is the error our model makes? Just tell me what is the error our model makes. Errors that our model makes are what's? Errors that our model makes would be called what's? Just tell me about, we want to do root mean squared error. I don't think we can get it from R squared. Residuals. Would you agree with me this is my residuals? So what do we want to do with the residuals? Square them. So now we want to take the mean of this. And now we want to take the square root of this. And there's the root mean squared error. I think we're doing a different model. There's the root mean squared error. And take a look. It might not be carrying all the decimals, but you can see right here, it should get the same number. It might just not be carrying all the decimals as we go through and do this. Let me see how many decimals I'm carrying. Looks like it should be carrying enough. It might be doing a small correction on it, but you should get about the same numbers. And that's the root mean squared error. Oh, no worries. That's the root mean squared error. So literally, mathematically, that's what it is. The root mean squared error. And so I'm just doing extra things to carry digits right there. So when we make confidence intervals, how do we make confidence intervals? A confidence interval looks the following way. Computer, you gonna be okay? A confidence interval as an estimate. And then you will do what? What do we do to make confidence rolls? So this is the estimate of the coefficient B sub I. Basically plus or minus 2, and it'll do the mathematics for us. It might be closer to 1.96 depending on degrees of freedom. That's more stat theory stuff. But it's basically 2, and the work is done for us. So it's basically 2. Not always. Closer to 1.96 for larger sample sizes. And then we need the standard error of B sub I, whatever B we're using. So to show this, we can actually prove it, or not prove, but show an example with this problem right here. Do you see how we have this? So let's take, this is our estimate of weight. So let's say estimate is this. Here's our standard error, is this. And now let's go estimate. And let's go plus concatenate minus error. I'll call it, oh, standard error. And what do we get? Check it out. How close is this to the interval? Pretty close. Oh, not pretty close. I was like, something's wrong. Oh my gosh. There we go. Let's clear screen to show it. There we go. Now it looks right. I was like, that looks weird. So now it looks a lot closer, but it's going to carry all the significant digits for us. This is what it's doing in the background for you by going plus or minus 2, but it's doing it for a lot more than just 1 now. It now gives you a confidence interval for every single coefficient in the model. So these are 95% confidence intervals to estimate the true coefficient of all the coefficients in the model. How would we know if a coefficient is statistically significant? How can I look at this and say weight is statistically significant in its model? How can I look at this and say x1 is statistically significant? I can look at x9 and say x9 is not statistically significant. I can look at x10 and say x10 is not statistically significant. I can look at x8 and say, yes, it is statistically significant. I'm looking at this and looking at this. I can look at x7 and say it is not statistically significant. I can look at x6 and say it is not. Yeah, I guess it's not also. x5 is statistically significant. x4 is statistically significant if 0 is contained in the estimate of what the coefficient could be. Because we're saying it might have no impact if we think it has a 0 coefficient. So we're saying, is 0 a possibility? Just think about this. You're asking yourself, what might be the true coefficient for the model? And Veda's got it right there, and Charlie's got it. We're saying, is 0 contained in the estimate of what the coefficient might be? And if 0 is contained in the interval, then it's not statistically significant. If 0 is not contained in the interval, it is statistically significant. Excellent work. The presence of correlation among predictors means that there is redundant information. Ooh, I love some redundant information. Which means we might have more uncertainty. It's like if you have 10 friends. I'm ready for a rematch this winter for Steph and Brian from the summer. Oh, Andrew, it's good to see you. Just on my say, awesome. Check this out. You ready? Quick break right here. If you're ready for a rematch. That's all I got right now. I just want to do that effect again. Okay. It blinked around. Where'd we go? Okay. So variance inflation. What is variance inflation? Go to review variance inflation. Variance inflation right here are VIF, variance inflation. To find the variance inflation, we simply run VIF, and I do have the right model in here. So what is variance inflation? Variance inflation is a measure of how much more uncertainty we have due to x's explaining each other. You do not want your x's explaining each other. To calculate variance inflation, which takes more time than we want to do usually, you'd have to do the following. You'd have to make a model right here. I can do it quicker, I think. You'd make a model. That should do it. With one of your x's being the y variable. And now this down here This r squared right here is the amount of variation in the x what? This r squared right here, which we don't like, is the amount of variation in this x, x1 what? Think about it. Just look at how it looks. This r squared right here means 31% of the variation in x1 is what? And that's how we calculate the VIF. And we'll do that right here next. And what does this mean, Charlie, to say 31% of what is explained by the other x's? That means there's overlap. It means these x's explain 31% of the variation in this x. If this was 100%, that would mean everything in x1 is redundant with the other x variables. If you saw 100% on here, that'd be horrible. That means x1 has no new information in it. So this is when we talk about do they bring new information, you don't want there to be redundant information where 31% of the information in x1 is explained by the other variables. Now, that's not actually that horrible. What you would do, and Charlie put the equation in the chat, you put 1 over 1 minus r squared and look at what we get. This value right here, and we'll put it up here in the hashtag, that value right there was the value we got right here. And it's going to calculate all the decimals and do it maybe a little more exactly for us. But that value is being calculated for us, but for every single x. X1 is explained by the other x's exactly, which we don't want. That means redundant information. That means our model is going to get confused. Now, if we want to know, and this is important things to know right here, about how much more uncertainty we have, this is variance inflation. Okay, variance inflation. Variance inflation equals standard error squared inflation. Standard error is our amount of uncertainty. So what should we do to the variance inflation to figure out how much the standard error has been inflated? Like if this is how much the variance has been inflated, how would I figure out how much the standard error has been inflated? Correct, Charlie. Yep. This is like, it just makes our model like, I don't know. It makes it more like, I don't like my model. We can still use it, but it does not invalidate the model. It means we just have more uncertainty, which we don't like. We don't like this, but we can still use our model. It's not like a huge violation of an assumption. It's just not good. So how could we take variance inflation and bring it back to just like, what could we do to both sides of this to just get standard error inflation? So think about what you could do to both sides of this mathematically to just find for standard error inflation. So look at the equation, variance inflation equals standard error squared inflation, because standard error squared is variance. So what could we do to the variance and the standard error squared inflation to make it solve for standard error inflation? So what can we mathematically do if we want to just know how much the standard error has been inflated? Because variance is standard error squared. So how can we just get standard error inflation? Good thing, no. Once you see, like, oh, it's just standard error squared, so let's just find the standard error inflation. So we know what the standard error squared inflation is. So this is equal to SE squared. What? Oh, I'm doing it the wrong way. Man, my brain needs to reset. There we go. So what could we do to the standard error squared inflation? We know what the standard error squared inflation is. We know what it is. Well, we just want standard error inflation. We don't want to know how much the standard error squared inflation is. We just want the standard error. And we just want, what should we do to it? Right now it's squared. That's the big hint. Just go back to algebra. Think to algebra and be like, well, since it's squared, if we just want to know the standard error, because this is standard error squared right now. There we go. Square root it. If it's squared, just square root it. So if we don't want it to be squared anymore, let's just square root it to find out how much the standard error inflation is. Now we want to ask ourselves, is this too much? So in our model, we can find out how much is too much variance inflation. We explain 70%. So we explain 70% of the variation, 70.15% of the variation. So we can then use this equation right here, which it shows you, to take the model's r squared and there's the R squared right here, and plug it in, and then according to the model, a VIF larger than 3.35 would be too large. Are any of our VIFs too large? There's always going to be overlap. When you invite a bunch of variables to the model, they're always going to kind of overlap in what they do to some degree. So do any of our variables have too high multicollinearity? That's another name for what we're talking about. Do any of our variables bring too much redundant information such that we're concerned, would not invalidate the model, just becomes sort of a concern that we're bringing a bunch of variables that do the same thing? Do any of the variables have too much redundant information with what we've calculated? Oh, you're welcome, Matthew. Thank Matthew. Man, that means a lot to me. I appreciate that. By the way, we talked to email recently, didn't we? I appreciate it. Today I'm doing a lot better. Doing a lot better. I need to have a second cup of coffee, but doing a lot better today. Like it's worlds better today. I took a little bit of medicine today, doing a lot better. Worlds better today. So, and I really appreciate all the well wishes. Everyone's been just so awesome to me. Man, did not expect on Monday to have surgery. Unexpected surgery is no fun. Yeah, on Discord. Yeah. So is this too high right here? It all becomes a blur sometimes. Did I speak to you on YouTube, email, or Discord? Are any of these VIFs too large? This is our model-dependent VIF too high cutoff. And the answer is none of these right here, are above 3.35, so we're fine. Oh, you got it, Matthew. I appreciate that, man. I was like, I'm doing this. I was gonna do it yesterday, but then yesterday kind of, yeah, it was. If I'm not appearing on camera, I'm struggling a little bit. So yes, none of them. They're all below 3.35, so we're doing fine. And we're doing fine today. All large VAF, there it is right there, is correlation among the predictors. Exactly. We don't have that issue. You should have found that X6, 7, 9 were not statistically significant. We did. Perform the partial F test. Ooh, we did not talk about a partial F test in class. If we only had a little more time. Let's talk about the partial F test and let's go through this. I'm going to put a big break in this video right here. Partial F is a major, major concept. And let's talk about what a partial F is. Partial F sounds like it's a really crazy thing. But the F test is used to test the significance of the model. What is the model with nothing in it called? Could you play a question for? Yeah, we can go back, Cassie. We can do that. I'm gonna start a new stream for 201 here in a second, Cassie. We'll do that afterwards. You bet, Cassie. And you might have to tell me what the question is because Canvas content switches around. So Cassie, we can do that. Thank you, Cassidy. What is the model with nothing in it called? What is the model with nothing in it called? The model with nothing in it. Nothing at all. Nothing at all is called what? Cassie, 100 points for swinging by here today. What is the model with nothing in it called? I thought the answer was points add viewers 100. What is the model with nothing in it called? Good thing we should know. Model that uses the mean of y to make predictions. No x's in it. It's called the what model? What do we call that model? It's a good thing to know. That model, doesn't know a lot about the world. If all the predictor values are set to their medians. Oh, you're talking about this one? Yeah, that's what we're doing right here, right? Yeah, we're gonna get to that in a moment. Yeah, Cassie, sorry about that. I thought you were talking about. I thought it said Canvas content. My brain broke right there, Cassidy. We'll be doing that here soon. You got it, Cassidy. Definitely. Thank you, Cassidy. The naive. The naive has no x's in it. It has no x's. But now we have the full model up here. And this is all x's. So let's do all x's. We'll change colors. The full model, or the complex, let's just call it complex. I think let's call it. Complex has all x's. And the naive has 0 x's. Has no x's. Going from the naive to the complex is the what? If you do a test from the naive to the complex, you're doing a what test? If you do a test from the naive to the complex, you are doing a what test? I'll show you it on the screen here in a second. Like we have 7 variables, let's say. Some model cuts out certain variables. Yep. That's what we do right here. We're going to see that in a moment. Yep. So if you go all the way from the naive to the complex, you are doing a what? If you go all the way from the naive to the complex, you have done a what now? I'll show you it on the screen. If you go all the way from the naive to the complex, you've done a what? Not a partial, but you've just done the what? Not a partial. We're about to do a partial F-test. So you've just done a what by going from the naive to the complex by looking at the overall model, and that's on the very bottom of the screen right there. So you've done, and you can call it full. Yeah, that's just the F-test. Great job right there, Charlie, 100 points. So that's the F-test right here. So what does the F-test do? The F-test goes, it looks at the overall, and it's an ANOVA right there. Exactly. It's performed via the ANOVA. That's exactly right. So it's an ANOVA. It's an F-test looking at going from the naive to the complex. Does our model explain a significant portion of the variation? So it's all the way from no variables to the full model, asking the reduction of sums of squared error. Like, that's the more complex way to talk about it. So when you think about a partial F is going to do what? A partial F doesn't have to start where? What do you notice about any of these partial F tests I run right here? A partial F test, what do you notice about it? Partial F tests. Correct. And I'll be going through that. That is correct, Charlie. A partial F test, like if I do this right here, that's a partial F test comparing a model with 7 variables to 4 variables. A partial F test does what? It doesn't need to include all the variables. And it doesn't have to start at the naive. It could compare a model with 1 variable and 3 variables in it. You could change it so we could make it longer right here. We could say, let's do a partial F going from 1 variable to 5 variables. Does this make sense that these are partial F tests? This is going part of the way right here. So you can do this partial F test comparing a 2 variable model to a 7 variable model. This is part of the way here. The full F test always goes from naive to full, but this right here would be a partial F test comparing a model with 5 variables to a model with 7 variables. So we're always asking, does the inclusion of variables bring with it new information? Like in the full F test, if it's statistically significant, you would say I should use the what model. In the full F test, you would say, well, it looks like my this model is good if the model is statistically significant. And this goes to Charlie's question. In the full F test, would you say, oh, I should use the naive because my model is statistically significant? Or in the full F test, would you say, oh, the complex model brings with it new information that is unlikely by random chance, and because it is statistically significant, when we look at the full F test, which is here in this output right here, that is the full F test, going from the naive to the full model. There's the full F test. And what would you use then? Would you say, oh, let's stay with the naive, even though it's statistically significant? Not the naive being statistically significant, the reduction in sums of squares from the naive. So you would use the complex, I think you'll know that right there. So what are you looking at when you do a partial F test? You're looking at the reduction in sums of squares going from a what to what right now. Who can explain, if Brian does a partial F test this way, he's looking at a model with how many variables and comparing it to a model with this many variables, and he's seeing if there is a reduction in sums of squares going between this model to this model. I'm actually starting with variables in the model, calculating how much error there is, and seeing if we get a significant reduction in the sums of squared error. So it's treating this like the naive starting point. So the partial F test allows you to use a different starting point than the naive and go a certain length of variables by including more variables. It's still the same idea of an F test. So if we get statistical significance, it'll be because the new variables bring with them information that's unlikely by random chance, just like the original F test would compare the naive to the complex, and when we are statistically significant, the model brings with it new information. The partial F test, once again, allows you to start with any amount of variables and go up to any amount of variables and just go part of the way on this scale. Does this make sense, Charlie and Veda and anyone else right here? And we'll do in the next question very soon. But does it make sense what a partial F test does? It looks at subset of predictors, subsets, as we could compare a model with 2 variables to a model with 7 variables and be like, let's see how this works. So when we take a look, let's go run it right here. What we want to do is we want to go right here. Oh, we already give you all the code. What fun is that? There we go right here. Here's the ANOVA. The way this is written is compare the simple to the complex. And now these variables themselves were not the variables we removed, which were x6, x7, x9, x10, were not statistically significant. But here's the thing. Going from the model with 1, 2, well, we can count right here. There's 4 extra variables. Including the 4 extra variables would bring with it new information or not bring with it new information. Try that in the chat right here. Including the extra variables would bring new information or not bring new information. These variables were not statistically significant. You can see that. I'll rerun this in a second. But interestingly enough, those variables together do bring information or do not bring information. It would bring new information, and that's what we're seeing right here. So it's saying that the inclusion of these 4 variables would bring significant information, even though we see right here that x6, 7, 9, and 10 are not significant. Including those variables do bring with them new information that reduces the sums of squared error that is unlikely by random chance. So including these 4 variables right here, so the degrees of freedom right here are the inclusion of the extra variables. Those are the extra coefficients in the model. And yes, so I think we're right here. We're almost down to the big question. If you're wondering about that one. Make predictions involves creating a new data frame. Let's make predictions for profit for every x value equals its median and for equals its mean. Run the summary. So one of the quick things, I'm going to maybe write this quicker than we have down below. We need to find the mean and median for everything. Now this can be very tedious. If you go here to like mean or you do summary. Here's the summary, and you could go and grab these values and input them into this data frame right here. We're making a data frame where we need the x's, but might be able to get it. Let me try a few things. Ooh, look at this. There's the median. There's the mean. But I need it to go. I don't want to use this code down here. Oh, it does that. That's not fun. This is way more work than it should be right here. That's fine. Ooh. Oh, because it's text. Oh, so I have to use my method I was using. 2 seconds. Apply PL rows columns fun equals median. There we go. Now we need to take and store this as median. I'm not a big fan of if I can't do it with code. The apply function applies a function to rows or columns. Once again, you could literally just take and start copy pasting these numbers right here. So we've literally taken more time doing this where it says x5 and the first number, if you look right here, this number is the median. So we could literally have just taken this right here and plugged in the number right here. And I feel like I'm just going to make an error if I do that. Yep, see, I already made an error. We should have grabbed the median right here. And there's that number and the mean right here. I'm just going to see if there's a quicker way here in half a second. X6, the first number is the median. Second number is the mean. And X7, first number is the median. second number is the mean. You can uncomment these out or bulk uncomment. Of course, it's going to look all crazy like. There we go. Got to make your code look nice. Don't delete a comma. I feel like we could do it quicker, though, with this, though. I think it's got it. Is that the median and the mean for each one? Yeah, and then... row 1. Okay. There we go. There's the median, there's the mean. Yeah, it's got it. Okay. So this code right here applies the functions a little bit outside of our class, not like crazy outside of our class, but it applies to the data frame, and this chooses rows or columns. So I'm applying it to each column, which is each x variable, the function median. So I took the median of each x, and then I took the mean of each, and then I stored it into a data frame. So I made my own data frame. So rather than doing it this way and copy pasting numbers, I would prefer to create my own data frame. So once again, this is called toPredict because we're going to use it to predict. And we're going to go down here and use the syntax for predicting. And I think it's already good to go. Is it good to go? toPredict not found. I didn't store it. Now it's stored. So here we are. And why is it predicting this way? We're only actually predicting for 2 observations. What do we need in our model to make predictions? To make predictions using our model, we would need values for what? We're trying to predict profit. So to make predictions in our model, we would need values for what? So to make predictions in our model, we would need values for what? To make predictions in our model, we would need values for what? How would our model be able to mathematically make predictions? To make predictions in our model, we would need values for what? So just think theoretically right here, for our model to make predictions on profit, it will need values for what? Because it's writing a math equation. So to write this math equation and make predictions, it will need values for what? How can our model possibly make predictions? How could it solve a math equation? It would need values for what? What would it need? Thoughts? Well, let's look at our model again. The inputs, and what are the inputs? You are right, Veda. Veda, you got it. Another 100 points, Veda, you got it. What are the inputs for our model? You're right, it needs inputs. So what are the inputs? We'd have to give it what? You're right, inputs, and what are the inputs? The inputs it would have to have are what? It has to have inputs, and the inputs it has to have are all of the x's. So it has to have all x's. So if you look over here, great job, Veda, excellent work. And if you look at what I just did, I added 8. So now there's the first input, the second input, and the third input for each of the x's. So the reason is this is the first person at all time for each of these x's, and then the second person is after the comma, and the third person is, they have all the values of 8s. So now I have a third person being predicted right here, which has a value of 8 for each value of x. You can see that right here. If you look at them, they're 8, and they're the third person in each value. Like the third person's value of x10 is 8. And it's probably better if we look at this. The toPredict data frame might make some more sense. Look at this. This is person 1 with their values of the x's. This is person 2 with their values of the x's. And person 3, because of decimals and stuff, they're just 8, 8, 8, 8, 8, 8, 8. And remember how I built that going back to here where I built it this way. It's kind of weird how this looks this way because this is the column of data that you are seeing right here. So it builds it in columns. So you have to like flip your brain to look at it. But this right here is the third person in all instances as I go across. And here's the values for person 3, which was 8, 8, 8, 8, 8, 8, 8, 8, 8. So there's 3 people we're predicting, and each of these people have x's for us to make predictions on. So if we're predicting an individual, we would use the prediction. So whenever it says predict for an individual, you will use prediction intervals. If it says predict for the mean of the line, or for everybody, which is the mean of the line, you'll use confidence intervals. And I think that's got it. We're going to do a little stat to a 1 here soon. Feeling a lot better today. Might get that second cup of coffee between this. But what are some questions? Let me know. What are people thinking? Veda, did this help out a lot? I think partial F was the only thing we didn't do in class this week. So sorry. Lost a lot of time. But hopefully that makes sense. Feeling a lot more myself today. Feeling a lot more myself. Man. Take some more medicine here soon, but I'm not a big medicine fan. Usually I'm like, no medicine for me. I will never take medicine. But then you need medicine. You're welcome, Veda. Thank you so much. It was, I would say, Sunday, Monday, Tuesday were the worst. Hence why I canceled class on Monday. Didn't I? I canceled one class on Tuesday because I just couldn't. I was like, nope. That's when didn't know hydrocodone could make you dizzy. And I wasn't even taking that much. I took half of what they said. Half of what they said. I get seasick. I get car sick. I can't go on roller coasters. I get sick on roller coasters. Probably same way it works with pain meds and stuff too. Probably makes me sick and dizzy too much, too easy, too quick. But that's got it. A lot of great review in this video. Let me know if you have questions. It's all about reviewing. It's all about practice. It's all about asking those questions. Veda, I want to throw you another 100 points. Thank you so much. Just being here, asking those questions. And I'm sure a lot of people are going to benefit from your questions and just what we've done here today. We'll be back. I'm going to do some 201 here in a little bit. And that's what we got going on. Until then, everybody, bye for now. I'm feeling a lot better. Bye. Oh, wait, we're hitting stop streaming. No, we got to hit this over here. I don't remember how to do this anymore.